All right, we're going to start this video by seeing how a matrix can scale a vector. All right, so if we have this matrix 5, 0, 0, 5, and we have this arbitrary vector x, where the elements are x1 and x2. If we look at a times x, remember by matrix vector multiplication's definition, we linearly combine the columns of A using the elements in X as the weights. So x1 times the first column plus x2 times the second column is what A times X is. If we scale those vectors and add them up, then we get the vector 5x1 as the first element and 5x2 as the second element. And notice that can be rewritten as just 5 times the vector x, right? Because x is the vector x1, x2. So what we ended up doing by multiplying a times x is we purely scaled x by 5. Therefore, the matrix A scales all x in R2 when you do a times x. Let's look at another matrix, this time 5, 1, 0, 5. And again, we work with this arbitrary vector x. The elements are x1, x2. And if we perform the multiplication a times x, we end up getting as the first element 5x1 plus x2, and the second element is 5x2. This time, a scales x only if x2 is equal to 0. Notice if x2 is equal to 0, then the original vector is x1, 0, and the resulting vector from a times x would be 5x1, 0. So it gets scaled by 5 again, only if x2 was equal to 0. This time, not all vectors in R2 were purely scaled by the matrix A when you do a times x. And this leads us nicely into the ideas of eigenvectors and eigenvalues. Now, what are those? Well, any non-zero vector x, so x has to be non-zero, it can't be the zero vector. So any non-zero vector x that satisfies ax equals lambda x is called an eigenvector. So x is an eigenvector if it satisfies that equation. And the number lambda is called an eigenvalue. So lambda, that Greek letter, we call that an eigenvalue, is just a number. So that equation is the essential piece of this definition for eigenvectors and eigenvalues. This equation ax equals lambda x, another way that can be thought of as matrix times a vector equals a scalar multiple times the vector, like we just saw a moment ago. So if a vector x gets purely scaled by our matrix, and it's getting scaled by lambda, then x is an eigenvector, as long as it's non-zero, right? We don't care about the zero vector here. And the lambda, the scalar multiple, that A is scaling the vector by, that scalar multiple is what we call an eigenvalue. So let's refer to the matrix that we just saw a moment ago, the matrix 5, 1, 0, 5. And we saw that vectors that have x2 being 0 will always be scaled by 5. So for example, the vector 3, 0, if we perform this matrix times a vector calculation, you get 15, 0. That can be rewritten as 5 times 3, 0. And notice by our definition, that means our eigenvector is 3, 0, and our eigenvalue is 5. Because ax equals 5x in this example. Let's look at a new matrix here, 7, 1, 3, 5. If we multiply that by 1, negative 3, we get 4, negative 12. And notice that's a scalar multiple of the original vector 1, negative 3. It's being scaled by 4. Therefore, 1, negative 3 is an eigenvector. So that is our x vector. And lambda equals 4, that's our eigenvalue, because we have ax is equal to 4x in this example. Again, if we look at the same matrix, 7, 1, 3, 5, and this time multiplied by the vector 1, 2, you get 9, 13 as the result. And this is definitely not a scalar multiple of the original vector 1, 2. A way you can reason through that is that if it was a scalar multiple, then the first entry is being scaled by 9, because you have 1 times 9 being 9. But then you'd have to scale 2 by 9 to get 18, but it's not 18, it's 13. So it's not a scalar multiple of the original vector. So therefore, the vector 1, 2 is not an eigenvector. And this is what we'll see. Some vectors are eigenvectors for a matrix, other vectors are not, and we'll like to figure out which vectors are actually eigenvectors because the scalar multiple property of eigenvectors is a really nice property. So these vectors will form a special set, and this set of vectors is what we call eigenvectors. In the scalar multiple, the scalar that the vectors are being multiplied by when you do a times x, that's the eigenvalue, and we'll also like to find those values. One last note on this definition of an eigenvector and eigenvalue is that it only applies for square matrices. Right? So the matrix A has to have the same number of rows as columns, because if it didn't have the same number of rows and columns, then A would transform x into a different size vector, right? But AX is equal to a scalar multiple of x, so it transforms x into a vector of the same size, right? It has the same number of elements once you do A times x. And so that would only happen if A was a square matrix. So this whole time, whenever we're talking about eigenvectors and eigenvalues, the matrix A will always be square. All right, so now that we know what eigenvectors and eigenvalues are, let's try to figure out how to find eigenvalues, and then after we'll figure out how to find the eigenvectors. All right, so let's look at the matrix 7, 1, 3, 5 again, and let's find the eigenvalues of this matrix. So if we're going to find the eigenvalues of this matrix, then by definition, we need to solve AX equals lambda x. And we're trying to solve for lambda. So this is the equation we're trying to solve by definition of an eigenvalue. And we're going to do something kind of sneaky here. We'll introduce the identity matrix on the right-hand side of the equation, because the identity matrix times a vector is still that same vector, right? So 1, 0, 0, 1 transforms the vector x1, x2 into itself. So we haven't changed the equation here. Just it looks different now. But what it enables us to do is subtract the right-hand side to the left-hand side and factor out that vector x. And now we can actually perform matrix subtraction by first scaling the lambda through to the identity matrix. So multiply all entries in the identity matrix by lambda. You just get lambda on the diagonal. And we can perform the subtraction to get 7 minus lambda as the first element, then the 1 and the 3, then as the last element we have 5 minus lambda. So essentially we have our matrix A subtracting lambda on the diagonal. So this would be a great spot to stop and see all the steps that we've done and see if you can do it on your own too after you've seen this. And just notice that we transformed the original definition of an eigenvalue, AX equals lambda x, that's where we started. We were able to transform that and rearrange it into a matrix times a vector x equaling the 0 vector. And this is a homogeneous system. This is like a new matrix times x equaling 0. Now we know a solution to this equation is definitely the 0 vector, right? If x1 and x2 were both 0, then a matrix times the 0 vector is definitely the 0 vector. But remember, by the definition of eigenvectors, eigenvectors are non-zero. So we don't care about when x1 and x2 are 0. We care about when it's non-zero, right? But if we already know the 0 vector is a solution and we want to find the non-zero solutions, that means there's going to be an infinite amount of solutions. And in the previous video, we showed that if the determinant of the matrix is equal to 0, then there is an infinite amount of solutions. So using that fact about determinants, we're able to go from an equation that has x1, x2, and lambda being unknown to just trying to figure out lambda now. Because if the determinant of that is equal to 0, that means the above step has an infinite number of solutions. That means there's more than just the non-zero solutions, so we'll get non-zero solutions too. And that means the very original equation that we started with, ax equals lambda x, we'd be solving for x1, x2 there, and also lambda. All right, so all we have to do is take this determinant, which for 2 by 2 is AD minus BC. So there it is. And you can rewrite that after multiplying the factors through and subtracting 3 to get lambda squared minus 12 lambda minus 32 is equal to 0. You can factor that as lambda minus 8 times lambda minus 4 equals 0. And that means our eigenvalues are 8 and 4. Now this is really neat and another great spot to stop the video and see what we've done. We started with ax equals lambda x, and we solved for lambda in the end by solving when a parabola is equal to 0. All right, let's look at the same idea, but in general. So if we have ax is equal to lambda x, that's the equation that defines the eigenvalue lambda and the eigenvector x. If we're going to figure out what lambda is, what we did is we introduced the identity matrix on the right-hand side. So we have I times x instead of just x, but I times x is x, right? Because I transforms x into itself x. All right, and we subtract the right-hand side to the left-hand side of the equation. And so now we have it being equal to 0 on the right-hand side, since it was subtracted over. And you can have lambda times I first and then multiply by x. There's an x common to both the ax and the lambda ix, so we can factor out that x on the right-hand side. And so ultimately what we've done is rearrange the original equation, ax equals lambda x, into this matrix times x equaling 0. Right? It's this homogeneous system where the new matrix that we're considering is A minus lambda I. Right? That's essentially the matrix A, subtracting lambda, our unknown eigenvalue. So we're subtracting that from the diagonal of A. So we have a matrix times x equaling 0. We know this has an infinite number of solutions when the determinant of that matrix is equal to 0. And so we find the eigenvalue by solving that determinant. The determinant of A minus lambda I equaling 0. Right? Lambda is unknown, but you can calculate the determinant, solve for lambda, that makes that equal to 0, and that would find the eigenvalues for the matrix. Once you've calculated the eigenvalues, you can find the eigenvectors, x, by solving the homogeneous system. Right? A minus lambda I, that is now a known matrix because you solved for lambda. So you have the matrix times x equaling 0. So what vectors x satisfy that equation? Because whatever x satisfies that equation, that is non-zero vectors x that satisfy the equation, it would satisfy the original equation ax equals lambda x, because that's just a rearrangement of the original equation. And so those are the two most important pieces of this idea, is solving for lambda with a determinant and then finding x by solving the homogeneous system. And then lastly, in your homework, you'll see them use the name characteristic equation. And the characteristic equation is just that determinant equaling 0. And it's the equation that you're using to solve for lambda. So by convention, that's just called the characteristic equation. All right, we found the eigenvalues of the matrix 7, 1, 3, 5. So now let's find the eigenvectors corresponding to those eigenvalues. Right? So corresponding to lambda equaling 8. So what do we mean by corresponding? Well, by definition, we have ax equals lambda x. So we have ax is equal to 8x. So what vectors x are getting purely scaled by the matrix and getting purely scaled by 8? So which vectors are getting scaled by 8? All right. So we subtract 8 from the diagonal. Right? So there's a minus lambda I times x equaling 0. We can write the augmented matrix representing that. Because 7 minus 8 is negative 1, 5 minus 8 is negative 3. We augment the 0 vector at the end. We can reduce this matrix, and we get a row of zeros. So we just have x1 is equal to x2 is the meaning of the top row. We can let x2 be a parameter t, right, where t is any real number. And that means the vector x that corresponds to the eigenvalue of 8 is tt, and you can pull out or factor out that t to have t times the vector 1, 1. So really, any scalar multiple of the vector 1, 1 is an eigenvector, except when t is equal to 0. Because remember, by definition, eigenvector is non-zero. So any non-zero scalar multiple of the vector 1, 1 is an eigenvector corresponding to lambda is equal to 8. Those are the vectors that get purely scaled by our matrix A. If you do A times 1, 1, or A times 3, 3, or A times negative 10, negative 10, you'll see that that matrix vector multiplication always scales the vector by 8. All right, our other eigenvalue was 4 for this matrix. So we do the exact same thing. Subtract 4 from the diagonal, solve that new matrix times x equaling 0. We can write the augmented matrix representing that system and reduce it. I didn't go all the way to reduced echelon form just so I don't have to work with fractions here. But this means 3x1 is equal to negative x2. That's what the top row means, because the top row is saying 3x1 plus x2 equals 0. So it means 3x1 equals negative x2. So again, we can let x2 be a parameter t, where t is any real number. And that means x1, x2 is the vector 3t, negative t. And you can scale out and factor out that t. So any scalar multiple of the vector 3, negative 1 is an eigenvector corresponding to the eigenvalue of 4, right? As long as t is not 0, because we don't care about the 0 vector by definition. So notice the eigenvectors corresponding to the 8 is a line going through the origin in R2. And the eigenvectors corresponding to eigenvalue 4 is also a line going through the origin. So if you include the 0 vector, so if you have the 0 vector plus the set of eigenvectors correspond to one of the eigenvalues, that would be a subspace, and sometimes you'll hear the word eigenspace. So these eigenvectors, in addition to the 0 vector, forms a subspace. As an eigenspace is the proper name. And you can come up with a basis for each of those eigenspaces or those subspaces. Right? A basis for the vectors corresponding to 8 is just 1, 1. And the basis for the eigenvector, for the eigenspace corresponding to lambda equal 4 is 3, negative 1. Right? All you need is 3, negative 1 to represent the whole space, because any scalar multiple of that vector will give you all vectors that are eigenvectors. All right, we saw by definition an eigenvector is non-zero, but what about an eigenvalue? Can that be 0? Let's look at this matrix 6, negative 3, negative 2, 1, and find the eigenvalues. And take the determinant and set equal to 0. And you end up getting the simplified version of lambda times lambda minus 7 equaling 0. That means lambda equals 0 and lambda is equal to 7. It'd be good for you to verify all that math. But yes, you can have an eigenvalue of 0. And geometrically, what that means is there's a set of vectors that gets purely scaled by 0. That means those vectors really turn into the 0 vector since they're getting scaled by 0. So A transforms some vectors into the 0 vector. All right. So let's find the vectors corresponding to lambda equaling 7. Subtract 7 from the diagonal and solve this homogeneous equation. You get the augmented matrix and reduce it. You get 1, 3, 0 as the top row and a row of zeros on the bottom row. Now you'll always get a row of zeros because that means there's an infinite number of solutions. Right? So if you don't get a row of zeros, that means you probably did something wrong. So that's good that we have the row of zeros. That means there's more than just the 0 solution. There's an infinite number of solutions because we're concerned about the non-zero solutions. And the top row is saying x1 is equal to negative 3x2. So let x2 be the parameter t. That means you can write the solution as, in the end, t times the vector negative 3, 1. So any scalar multiple, as long as the scalar multiple is not 0, any scalar multiple of negative 3, 1 is an eigenvector. It gets purely scaled by 7 when you do A times one of those vectors. And you can verify that the matrix times the vector negative 3, 1 is getting purely scaled by 7. So you could check that out. All right, corresponding to lambda equaling 0, we solve this equation, and we're subtracting 0 from the diagonal, which just leaves you with the original matrix. We're seeing when what x solves this equation, and you get the augmented matrix and reduce it. I didn't go all the way to reduced echelon form just so we don't have to work with fractions again. And we have 2x1 is equal to x2 is what the top row says. And this time I'll let x1 be t so that we can write our solution for x1, x2 as t and 2t. And you can scale out that t to get the vector 1, 2. So any scalar multiple of the vector 1, 2 is an eigenvector. It's a vector that gets scaled by 0. These are the vectors that get multiplied. Do a times those vectors, and you get the 0 vector. And you can check that out, right? If you do a times 1, 2, you'll definitely get the vector 0, 0. And you can come up with a basis for each one of these sets of eigenvectors. And the first basis would be negative 3, 1. The second base would be the vector 1, 2. That's all you need to describe those. Really, they're solution spaces to that homogeneous system. They're a basis for the eigenspaces corresponding to those eigenvalues. All right, let's find the eigenvalues of a 3 by 3 matrix. So here's a particular 3 by 3 matrix, and it's the same exact process. It's just a bigger matrix. So subtract lambda from the diagonal, take the determinant of that, and set it equal to 0. Now to do the determinant of that, you'll have to use the cofactor expansion explained in the previous video. So if you do the cofactor expansion, I did it along the bottom row because that will be the quickest for me to do, because there's 2 zeros. So the more zeros there are in a row or a column, you'll want to use that row or column because it makes the cofactor expansion a lot faster. So there's the cofactor expansion along the third row, and we're setting that equal to 0. After some simplification, right, we get our cubic equation that we're trying to see when it's equal to 0. And I used a calculator to see when that cubic equation is 0. And it happens at negative 2, 4, and 6. So those are the eigenvalues corresponding to that 3 by 3 matrix. And you'll notice this pattern that if you have a n by n matrix, then you'll have at most n eigenvalues. Right? And it's because you end up solving a polynomial of degree n. Right? That's what the determinant of a minus lambda I gives you, is a polynomial of degree n. All right, let's find the eigenvectors for that matrix now that we know the eigenvalues. And I'll just find the eigenvectors corresponding to lambda equal negative 2. And I'll let you solve for the eigenvectors of the other eigenvalues. All right, we subtract 2 from the diagonal to get this homogeneous system. And we can write the augmented matrix that represents that matrix equation and get that matrix into reduced echelon form. And now the top row is saying that x1 is equal to 3/2 x2. And it's also saying in the third row, x3 is equal to 0. Right? That's the meaning of the third row. And so we can let x2 be equal to 2t here. I'm using 2t so that when I plug it in to the x1 equation, the 2's cancel out and I can avoid the fraction. And I'll get 3t for x1. So the solution is 3t as the first element, 2t is the second element, so that's why I'm letting x2 be, and x3 is equal to 0. I can scale out that t to get t times 3, 2, 0. So any scalar multiple of the 3, 2, 0 vector is an eigenvector. All of those vectors are being purely scaled by negative 2 when you do a times one of those vectors. So again, the set of vectors here, when you include the 0 vector, you get a subspace that we call an eigenspace. The basis for that subspace is 3, 2, 0. Now let's look at a eigenspace that ends up having a dimension of 2. I mean, everything so far had a dimension of 1. All of those sets of eigenvectors were just lines through origins. In this example, for finding the eigenvectors of this matrix, we'll see that the eigenspace has dimension 2. It'll be a plane through the origin instead of just a line. All right, so take the determinant of a minus lambda I and set it equal to 0. You'll get a cubic equation, and you'll have the eigenvalues be just -3 and 3. So you only get 2 eigenvalues for this matrix. You could call the eigenvalue of 3 having multiplicity of 2. When you look at that cubic equation, you see the factor lambda minus 3 being squared. So sometimes you'll see that called multiplicity of 2. But for our purposes, we just have 2 eigenvalues, and it's -3 and 3, right? There's some set of vectors that are getting purely scaled by -3, and some set of vectors are getting purely scaled by +3. So let's look at the +3 eigenvalue. Subtract +3 from the diagonal, solve that matrix times that equaling 0. So we augment the 0 vector at the end. We get it a little simplified there. We're subtracting that 3. Reducing it, we would have 2 rows of 0. So that means the top row is saying x1 is equal to x2 minus x3. Because the top row is saying x1 minus x2 plus x3. So rearranging that to solve for x1 is x1 equals x2 minus x3. And so this time we need 2 parameters. Let x2 be s and let x3 be equal to t. Right? x2 and x3 are free to be anything. So we'll call them s and t, where s and t are any real number. And so you can write our vector as s minus t, as that's what x1 is, x2 is s, and x3 is t. And you can separate that into 2 different vectors, one being scaled by s and one being scaled by t, right? Because the first 2 elements have an s, and the first and third element have a t. So the solution can be rewritten as s times 110 plus t times 101. And we see that since s and t can be any real number, right, this is all linear combinations of those 2 vectors, and those 2 vectors are definitely linearly independent. So all combinations of those 2 would give you a plane going through the origin. It means all vectors that lie on that plane are eigenvectors that get purely scaled by 3 when you do a times any one of those vectors. So the eigenspace has dimension 2, and a basis for this eigenspace would need 2 vectors, right? The vectors 1, 1, 0 and the vector 1, 0, 1, right? Those 2 vectors form the basis for my eigenspace. All right, well, there's quite a few examples of finding eigenvalues and eigenvectors of different matrices. I hope that all makes sense. And that's it for this video. Thank you.